Welcome to our final in a three-part oceanography lecture. Today we're going to be looking at waves. In particular, we're going to focus on wind waves, which obviously are caused by wind, tidal waves, which are caused by the gravitational attraction of the moon and to a lesser degree the sun, and lastly, tsunamis or seismic sea waves. To begin, waves transfer of energy. A water wave moves in an orbital motion, so there's no net displacement of the water as energy travels through it. When you look at a wave, the crest is the high point and the trough is the low point. The amplitude is the height of a wave. Amplitude can be positive or negative, and the baseline is the resting state. Waves, like sound, amplitude can be analogous to the volume. Light, amplitude can be analogous to the brightness. The wavelength is the distance between 2 points on adjoining waves. 2 crests, 2 troughs, but 2 points. So basically it's the length of the wave. And the frequency or cycles per second is how many waves pass by. The pitch of sound would be frequency. The color of light would be frequency. The number of waves that pass by any given second. The measurement is hertz. You've heard of megahertz in radio and TV waves. That's the metric prefix mega in front of the unit hertz, but cycles per second. Incidentally, wave period, or the time it takes for a wave to pass by, is 1 over the frequency, or the reciprocal of the frequency. So the 3 aforementioned waves are shown below, with the period or time it takes for a wave to pass. You can see wind waves generally fall between 1 and 30 seconds per wave. Earthquake or storms, earthquake would be tsunamis, and storm surge is really half a wave, but they are somewhere in the neighborhood of 5 to 10 minutes per wave. And the sun and moon has 2 distinct waves, the tides, that is. A 12-hour period or a 24-hour period. That would be a semi-diurnal for 12 or a diurnal for 24. That is not exactly 12 hours or 24 hours. It's 24 hours and 50 minutes. Or 12 hours and 50 minutes exactly, but we will get into lunar days and solar days a little later in the lecture. The speed of anything is really distance over time, that's rate, and in a wave we have 2 ways to calculate speed. The first is the wavelength over the period. The second is the wavelength times the frequency. Remember, the frequency is the reciprocal of the period. Waves interact with each other when you have more than one wave traveling through a medium. We call that interference. You can have destructive interference, which cancels out the energy, resulting in a reduced wave or no wave. Constructive interference, which builds larger waves. That constructive interference could lead to rogue waves, which would give you larger than expected waves. This causes trouble when it comes to ships, boats, docks, things along those lines. The illustration here shows you the net result of interference. waves are bent, we call that refraction. With light waves, we use lenses to bend light, focus it. Water, if you stick your hand in, your hand is distorted because there's refraction from the light. But when it comes to ocean waves, the bottom causes waves to bend when you have interference with the bottom, and they tend to bend towards the shallows and disperse through the deep. And then diffraction would be as waves travel through a pass or are interfered with by islands or other barriers. We talked about rip currents in the video. When you do your oceanography assignment, we have various videos, and we discuss rip currents. And here's an illustration with the return flow of water. That bouncing of waves is reflection. That does cause some rip current. I've also seen waves bounce off the seawall and interact with each other, causing higher than normal waves. We mentioned orbital motion. Now, this illustration shows you that the orbits have a depth of 1 over the wavelength, and then there's no more energy travel. So the deeper you go, the less rocky that wave gets until you reach half the wavelength, and then there's no more wave. So this is important when we look at where waves break on shore and the coastal processes we're about to address. So the orbital diameter becomes negligible at L/2, or half the wavelength. When water depths exceed half the wavelength, the wave travels unencumbered. So what causes waves? Well, we mentioned wind, gravity between the moon, lesser degree the sun, and our Earth itself, and then seismic events, meteorites, underwater landslides, even humans testing nuclear weapons underwater have caused seismic waves. Now, the height of your wind wave is determined by the strength of the wind, how long the wind blows, and the distance it blows over. That's called fetch, the distance it blows over. This is the Beaufort scale of wind. You can see knots, which is nautical miles. Nautical miles, the knot is based on 1 minute of latitude, whereas miles per hour is based on a statute or land mile. And you can see the effects at sea, the effects at land, and the description. So smooth as glass really doesn't exist. There's always going to be some sort of capillary wave due to surface tension, maybe a breath of air. But this is as smooth as water will get. You can see that is a negligible amount of wave action. Now, a swell is when the wave does not break because you have a deep or steep entrance, and then it hits the side, and you can see that is an image of a swell hitting a seawall. Waves break at half the wavelength. The bottom interferes with the wave, and the wave topples over. That's called the surf zone. So half the wavelength is where waves break. When a wave breaks, it's also termed a white cap because, it turns white and frothy. Half the wavelength is the depth. There's 3 types of waves that we see. We see the spilling or rolling, the plunging, or the surging. Take a look at the illustrations. Here is spilling breakers. Plunging breakers are much more violent. You can see those surfers having a go of it. None of them look very successful in this image. And the surging breakers are typical of a very deep, steep beach, sea cliffs in the background, and you get a lot of swells and surging breakers in these areas. So here on the Gulf, we're not prone to these surging breakers because we have a shallow, wide continental shelf. We're not prone to the larger surf here. Shoaling is when your wave breaks offshore due to a sandbar or some other impediment that makes it shallower a little bit offshore, and you can see the waves break, and then you have a gentle beach. Now, a storm surge is half a wave because the low pressure pulls a dome of water up. If your storm surge is coupled with a high tide, you can have real problems, though, and that's the fear for our coastal communities here. If you have several feet of tide and several feet of storm surge, you have 2 times several feet of flooding. A setch is an enclosed wave in a basin that gets harmonic motion. Now, our next type of wave are the tides, caused mainly by the moon. The sun plays a role. This is Mont Saint-Michel in France, and this is an extreme example of tidal influence on a coastal town. It's a tourist attraction because you have an island or a peninsula, and it's one of those anomalies that people like to visit. But a tide is that cyclic rise and fall. Notice the image. You have 2 bulges of water. The one closest to the moon is the gravitational tide. That's labeled A. And C, we generally refer to as the inertial tide. So you have 2 tidal bulges, which means many places on Earth get 2 highs and 2 lows during a tidal day. Tides are called forced waves because they're stuck in attractive force. So they're never free of that force that caused them. They're a forced wave. And tides are caused by gravity and inertia. So gravity causes one bulge and inertia causes the second bulge. Now, the Earth, Moon, and Sun have a more complicated relationship than you would think, because the center of gravity of the Moon Earth system is not the center of the Earth, and the Moon exerts gravity on the Earth as well. Earth wobbles in its orbit as the Moon revolves around it. So the Earth, Moon, Sun relationship, Earth moves back and forth in its orbit as it takes its path around the sun. This affects tides. This affects a lot of things on Earth, actually. And our tidal bulges are formed by, as we said, gravity, inertia. So the moon's gravity attracts the ocean towards it. And then the second inertial force pulls the water away. And take a look of the Earth's center of mass is not exactly in the center because of the Earth-Moon system. So here you have gravity and inertia, just another way of looking at it, hoping that you understand the physics behind it, just a little bit of it, that the gravity does cause one bulge and the inertial causes the other. It's also called the centrifugal force. If you want to picture it, picture driving and then taking a sudden turn and everything sliding on the dashboard of your car. That is inertia. Our tidal cycle, like I mentioned, is not exactly 24 hours because the whole system is moving, and as the moon goes around the Earth is also rotating on its axis. So it's 24 hours, 50 minutes. That means the moon rises and sets 10 minutes every day, 10 minutes different every day. So you have 24 hours and 50 minutes is termed a lunar day or a tidal cycle. So when you're talking about a semi-diurnal tide, which is twice a day, it's 12 hours and 25 minutes between cycles. When you're talking about a diurnal, it's 24 hours, 50 minutes. Also, the moon is not going around the Earth equatorially or even with its obliquity, which is the tilt. So you have three distinct possibilities. You have one high and one low every day. We call that diurnal. You have two highs and two lows every day of relatively equal height. We call that semi-diurnal. And then you have something in between, which we call mixed. Here you go, semi-diurnal tides, diurnal tides, mixed tides. Now in the center of our ocean basins, we have, like it's a giant setch, and we have that amphidromic point, which is a node where there's no tidal influence. So our semi-diurnal tides are two highs, two lows every 24 hours and 50 minutes. Our diurnal tides are one high and one low every 24 hours and 50 minutes. And of the mixed tides are a combination. We have a mixed, predominantly semi-diurnal tide here on the Gulf Coast of Florida. This is an important image to understand. You can see there's our Gulf Coast right there. And the west coast of the United States have mixed tides. You can see the two tides of different heights during the lunar day. Much of the Gulf has diurnal, one high and one low per day. And then the eastern seaboard, most of it is semi-diurnal, two highs and two lows per lunar day. So this is a snippet off the internet from St. Petersburg, Florida, showing you a mixed semi-diurnal tidal cycle. We have two highs, two lows, different heights per day. Now, the next is the sun. Remember, most of it's moon, but the sun does have some influence. And when they are in a straight line during the full or new moon, the gravity between the sun and the moon are working together, and you have the largest tidal bulges. When they're in opposition during the quarter phases, the gravity is working against each other, so you have the least or moderate tidal bulges. So the spring tide occurs when you have the greatest tidal bulges. Spring tides, the lunar phase, full and new moon. Incidentally, marine organisms time their reproductive cycle on spring tides because the larvae and eggs are distributed on the tides more. And of course, any good fisherman knows fishing on these new and full moons are more productive because the laying of eggs and larvae present makes the fish feed more, meaning that your bait will be more apt to be chased as well. The neap tides during the quarter moon phases, less water movement, less water flow. So here's something to look at. We'll look at the lower Australia first. That is a mixed with a semi-diurnal influence, similar to what we have here. I want you to look where it says neap tides, days 17 through 20. You can see how the tidal period breaks down, and you have very irregular tides. Okay, it's not the amplitude's a lot less, and then you can see on the 18th you only have one tide, and on the 19th you kind of have a pause, a slack, and then it goes up. Where the spring tides are pronounced 2 highs, 2 lows every day. So a mixed gives you different heights and then tend to break down during the neap cycle. We get that here. Now, when you look up top, you can see that is the eastern seaboard. That is a semi-diurnal, and you get 2 highs and 2 lows daily. The amplitudes are highest on the full moon spring. They're low, a little lower on the new moon spring, but still relatively high. And the neap tides, the amplitudes are far less. So to look at it at charts like this, if you see 1 high and 1 low per day, you know it's diurnal. If you see 2 highs and 2 lows per day, you know it's semi-diurnal. If you notice during the neap tides, things break down and pronounced height differences between many of the tides, you know it's a mixed tide. Now, in basins, you have very different rules because you're forcing a lot of water through a small area. Think of John's Pass and all the current. All that tide from the Gulf is pushing through that little opening and then coming out that little opening. There's definitely a time delay and definitely a lot of currents. So confined basins are famous for currents and delayed tides. The last type of wave are tsunamis or seismic sea waves. The amplitude of a breaking seismic sea wave can be over 100 feet, so you have to get to higher ground. When the seismic sea wave is out to sea, the amplitude could be a meter or two, but the wavelength is huge. So seismic sea waves are interesting, whereas they have a giant wavelength and very little amplitude in the open ocean, but then they, when they hit that L over 2, that giant wavelength topples over hundreds of feet. So here's the speed, the general speed of your tsunami in the deep ocean is somewhere on the order of 500 miles per hour, maybe 6. When it hits shore and breaks, you're still moving very fast. You can be in the neighborhood of 200 miles an hour, whereas a wind wave, much slower, much less energy. This is a little dated, this image, but these are some of the major tsunamis. And I chose this image just to show you that most of it is around the Pacific Rim because you have subduction very deep. You're not getting them in the Gulf of Mexico because we have that long continental coast that would break way out to shore. Also, Indonesia is a very tectonically active area and very prone to tsunamis as well. So we do have a tsunami warning system. 26 nations monitoring the activity of seismic sea waves because remember, get to higher ground and you're safe. So the key is detection and then alarm and then evacuation. So buoys, because buoys detect the water motion, is the common way to record the wave heights, and that data is then relayed to a satellite and then relayed to different stations all over the world.